All right, everyone, let's get started. Today, I'm pleased to introduce to you Manan Tomar. He's an incoming PhD student here at RLAI, starting with Professor Matt Taylor this fall. Over the past year, he was a resident at Facebook AI and will be telling us about the school work that he did there, which he also presented at ICML RPL last month. All yours, Manan.
All right. Thanks, Abhishek, for the introduction. Thank you, everyone, for coming in. This is this work that I presented recently, did at Facebook AI Research last year with Jonathan Efroni and Mohammad Ghamzadeh. And it's called Multi-Step Greedy Reinforcement Learning Algorithms. So let's get into it. Just to introduce what we mean by multi-step greedy policies, let's start by looking at what the traditional policy improvement definitions says about a one-step policy improvement. So we have the reward function and the value function of the successor state, and we try to maximize over the one-step actions to generate a new updated policy. We can look at a similar 8-step generalization of this process, which has been present in the literature for quite a while, in which what we try to do is solve an H-horizon finite step problem, wherein we've included the rewards till the 8th step, and then we substitute the value function after the 8th step. The idea is to maximize over all of these non-stationary policies, H non-stationary policies, and then use pi naught as the output policy, and then repeat the process. So once you're familiar with this definition, everything else should be really smooth. We can easily, from the 8-step definition, we can easily come down to the kappa greedy policy definition. And what we've done here is essentially just taken a kappa weighted geometric average of the 8-step returns from the previous slide. So I have 8-step returns for each time step. If you geometrically average them for multiple time steps till the end of the horizon, we get this sort of a definition in which this is a simplified version. If you just follow the math, it's pretty simple to bring it to this form. And what we have is essentially a problem with a discount factor of gamma kappa and a modified reward which looks like RT plus gamma times 1 minus kappa times the value function of the next state. If there are any doubts regarding this definition, you can please ask now. I think that'll be better. And then we can move on to the next slides. Okay, cool. So now let's look at what happens when we use this form of a policy update in traditional policy iteration, which we call now kappa policy iteration. We update the policy for these n kappa number of time steps. The first step is evaluating the value function, which remains as it is in terms of traditional policy iteration. The second step is where we make this change of solving a different MDP, in which we say the discount factor is shifted to gamma kappa, and we have a we have a shaped reward as well. Everything else in this MDP, in the surrogate MDP, remains the same. The dynamics remain the same. The actions remain the same, as well as the state space. This minor change will allow us to solve the kappa policy, kappa greedy policy, in the usual format. Okay. And yeah, one more thing to note here is that if we have kappa equal to 0 here, it basically gives us spectrum of different kappa values. If we have kappa equal to 0, then we again boil down to the one-step definition of policy iteration. If kappa is equal to 1, then we are essentially saying that we want to solve the original problem in one step. And any value in between will give us an average of different multiple step updates. Okay, so let's plug that in inside any RL algorithm, and let's see how that looks. So what we call as kappa pi based RL algorithms, it basically has three steps. One is we do multi-step policy improvement on the original MDP, and this step is exactly equivalent to solving a surrogate MDP with a different reward function and a different discount factor. The second step is evaluate the policy on the original MDP to generate V pi I. And note that V pi I is again plugged back into the into solving the surrogate MDP. So that's why we require this policy evaluation step. And then we just repeat these two processes. And in this way, it's good to look at any RL algorithm in this sort of a structure where we've brought it down into a policy iteration or value iteration scheme. Till now, whatever I've been discussing is based on policy iteration. We can do the same sort of steps for value iteration as well. And you can have a look at the paper if you wanted to see the detailed algorithms for that. Okay, so we've defined a basic framework of the kappa pi based RL algorithms. Now let's plug in one of the solvers for this surrogate MDP, which in our case we've chosen to be DQN or TRPO. So that results into the algorithm which we called as kappa pi DQN. And the idea is very, very simple. It's just solving the surrogate MDP with DQN. So again, we have two steps, policy improvement and evaluation. And inside the improvement step, we have this DQN-based solver, which is trying to just solve this MDP that has a different reward function, a different discount factor. And it generates the policy based on its own Q function, which is Q theta. When we get out of this loop, we have this evaluation step in which we are trying to estimate the current policy's value function, which we call as Q phi. And we generate, because in solving the surrogate MDP, we require V phi, and here we are solving for Q phi. We get V phi just by plugging in the current policy's actions to get V phi. And this is done just to be just to stay intact with the workings of DQN, because DQN deals with learning Q values. We do the same here. So yeah, that's a very simple way to enhance DQN into this framework. And we can do the same sort of thing with TRPO for on-policy cases.
Question?
Yep.
With one-step methods, you don't need a model of the world. But with these n-step or k-step, h-step
right.
Methods, don't you need a model?
You don't. It's I actually didn't mention this before, but it's actually just like TD lambda, doing TD lambda for the improvement stage. Okay. Here. So instead of the evaluation case, instead of doing this multi-step update for the evaluation, we are just doing multi-step updates for the improvement case. So we still don't require the model here.
Why don't you require the model? You're looking ahead several steps. You have expectations in the update. Why don't you? I don't see how you've escaped the need for the model.
Right. Okay. So in the exact case, if we are talking about the 8-step version, then we do require a model to solve for this max operator across these H policies. But in this kappa-based definition, we are saying this is equivalent to solving another MDP with this reward function. So if we do have a value function estimate here, then it just boils down to solving another MDP with the reward and dynamic with the discount factor changed. Okay. So once we have this, for the TRPO case, again, we're going to do the same thing. We're going to improve the policy with respect to the value function V theta, which is the local value function of the surrogate MDP. We have these modified reward and discount factors. And then we update because TRPO also requires an update for its own value function. we update the v theta based on this return, which is different from the original MDP's return. And then once we have that policy from TRPO, at each step we evaluate it, which is v phi, which is based on the original MDP's return. Okay, so let's discuss the experimental setup once. Now, this is all good, but what we need to do here is essentially solve these updates for eternity. The ideally we have to solve the inner surrogate problem forever to get the actual solution. We can't do that because we are bounded by the number of environmental time steps we can take. So we have to define some sort of a parameter to a number of steps in which we need to assign the surrogate MDP for, and to do that we take slight inspiration from the theory, the convergence theory of these algorithms, kappa-based algorithms. And what we say is n kappa is a function of the final accuracy that we try to achieve. So if our accuracy is 90%, we'll have some value of n kappa there. And n kappa is basically the number of time steps we want to run this policy iteration scheme for, which basically means that if the total number of environmental time steps is t and we want to run it for n kappa time steps, the surrogate MDP should be run for t kappa time steps at each policy iteration time step, policy iteration iterate. So this is how the simple table will look like. If you have different kappa values, the t kappa value will differ. And the rationale here is that if kappa is 0, if kappa is small, then we are trying to solve at each iteration a very heavily discounted problem. So we do not need to assign too many time steps into solving it. And if kappa is high, again, this problem is more difficult. So let's assign more n kappa times, more updates to solving the surrogate MDP. So once and this is based on the kappa values that we've chosen here are based on a logarithmic scale, and we'll use the same values to in our experiments. So this is how the results look like. These are the Majoko results. We have two baselines here, which I've denoted by n kappa equal to t and n kappa not equal to t. What I mean by that is one baseline is essentially saying that when kappa is equal to 1, we boil down to dqn or TRPO. So all of the red curves are the baseline algorithms that you would naturally compare to. The other baseline is called n kappa equal to t, which basically means that I'm just allowing one time step to solve the surrogate MDP. So therefore, the number of time steps I'm running the policy iteration scheme for is just the number of time steps I've gotten from the environment. So that is another naive baseline. And what we want to show is it's necessary to solve the surrogate MDP beyond a certain time steps to show real gains on the performance. So although you have better performance compared to TRPO, even in this case, the gains are higher when you try to allocate much more budget at each iteration, which is the second row. Yeah. All right. And then we have similar results for Atari. In all cases, we see that a different kappa value shows better performance, just as this was in the case in TD lambda. And yeah, and this is the sort of results we have in the table. We have the best performing kappa value. What happens when we set kappa equal to 0? When we set kappa equal to 1, we retrieve the baseline dqn or TRPO again. And when we set n kappa equal to t, what kind of best value of kappa performs the best here? We have a similar table for TRPO and the value function value iteration algorithms in the paper. And lastly, we added one more comparison, which is with respect to lowering the discount factor of the problem. So this is related to a paper by Bruno Scherer, in which the idea is to basically bias the solution by discounting the problem discounting the problem heavily. So if the original solution, if the original problem is about solving the MDP with a gamma value of 1, let's try to see what happens when we discount the factor, discount the discount factor to some value of 0.5, say, and test it on the value of gamma equal to 1 eventually. This is, of course, biasing the solution, but let's see what happens there. So they've shown that this actually improves performance in a lot of cases. And why is it similar to our problem? That's because if you go back, we see that this definition of surrogate MDPs is essentially doing something like that. So we have this have a more heavily discounted gamma here, which is gamma kappa instead of gamma. And it does have that flavor in which we say, okay, we are sort of discounting the problem heavily at each iteration. Of course, we are also shaping the reward at each time step, so that removes the biasness of the problem. And if we do that sort of a comparison, then we see that although discounting helps in some cases, majoritarily in Mojoko domains, it does not do that much better in Atari. And even in Mojoko, the gains that you see are inferior to the gains that you see when we deploy the multi-step greedy algorithms. So this is, again, an interesting comparison with our case. And the TRPO, lastly, the TRPO, Kappa PI TRPO algorithm has interesting connections to GAE, which is called Generalized Advantage Estimation. And I think this has been used a lot alongside TRPO and PPO in terms of all practical purposes. So that's a neat point, but GAE doesn't offer a solution in the DQN setting, suppose. So I would say this is a much more general way to propose multi-step updates. And of course, this should be a good addition to a lot of toolboxes, RL toolboxes, because the performance gains are quite prominent. And eventually, what I like about it is that you can think of all the RL algorithms inside this umbrella scheme of policy iteration and value iteration. Thank you for listening. That was all.
Yeah, so Matt has a question in the chat. So he doesn't have a mic or video right now, but he's asking that if this time, could you talk a bit about the difference between what you proved or reasoned about theoretically versus what you showed empirically in this deep RL setting?
Okay. I don't. So this paper really doesn't have a lot of theoretical component to it. We've borrowed a lot of stuff from the theory, like the allocation of n kappa, the number of iterations we need to run for solving the surrogate MDP. That is derived from the convergence proofs, but it's not exact, of course. And most of the paper is empirical. It's just based on the idea of solving multi-step greedy policies. So yeah, I wouldn't say there's not a lot of theory involved. This is a completely empirical paper. I don't know if that answers Matt's question or not. Okay, great.
Yeah, maybe I can add to the question. Maybe it's more about okay, maybe I'll just ask a related question, which is so in like n-step methods or lambda returns, you have some intuitions as to when you want to, like, given a problem, maybe you can do some reasoning about whether this will require setting lambda as high or low.
Right.
It should be close to P, should be close to Monte Carlo. So while running all of this, did you get some kind of intuition about kappa?
Yeah, definitely. So in general, for Atari-based games, the best value of kappa was on the higher side, and for most of the Mujoko domains, it's on the lower side. I think that's because the Mujoko domains are inherently solving a short horizon problem. So, suppose if you take walking for example, it is a short horizon problem. So heavily discounting the problem uh, doesn't really create much trouble there. It actually improves performance. That's what we saw in the experiments where we lower the discount factor directly, Ant and Walker sub, for example. That's one intuition. Although the caveat here is there is no one kappa value that worked best for all experiments, even in individual domains like Atari, Mujoko. So I think this would reach a really the best way forward with this work is to have an adaptive version of kappa, which basically changes across the training procedure. But we are unsure about how to do that. For now, it's just about choosing some range of kappa value that works best for all the Atari games, suppose, which is fairly reasonable. There is a decent range in which the gains are prominent. Yeah.
Cool. There's another question in the chat. It says
Yeah.
that weekend version uses two value functions and experience replay buffers. So that's one. And are online versions possible similar to Q Lambda?
So the Deacon version uses just one experience replay buffer, but yeah, two value functions, two Q value functions, one for the surrogate MDP and one for the actual policies update. And it actually uses 4 because you have target networks as well. But that's a minor issue. And what was the other question?
So the other question was, are online versions possible similar to TD Lambda, Q Lambda?
I've not actually looked at that yet. I would say yes initially, though. Yeah.
So I'm still totally thrown by you're calling this a multi-step greedy algorithm because you
Right.
say it's a model-free algorithm,
Right.
and the concept of multi-step greedy algorithm seems inherently a model-based idea. You're going to look ahead multiple steps. You need a model to look ahead multiple steps.
Right.
I don't know what the resolution is. I believe your method is model-free, but I just don't. It seems wrong or at least strange to call it a multi-step greedy algorithm.
So I say it's multi-step because it derives from the multi-step ideas, and it's model-free because at each step we are only talking about solving uh, any black box solution, which basically solves the surrogate MDP for us. So ideally, we would like to have a model-based solver for that black box, but in our case, we're solving it approximately. So that's where the DQN or model-free part comes in.
All right. There's another question. If you had an exact solution to the evaluation step, it would be an exact equivalence to the model-based multi-step greedy version.
Yeah, yeah, exactly. And also, yeah, one more point is that it's not exactly solving the 8-step problem. So it's not exactly solving the multi-step problem. We've also, there is one step in which we've reduced it to the average of all 8 steps. So yeah, I mean that's where we get the surrogate MDP's definition from.
Could you elaborate on that point?
What I mean is, although we start from the 8-step generalization here, we are eventually taking averages across all 8 steps, and that's what allows us to define this surrogate MDP based on kappa. So it's not exactly the 8-step return.
All right. If there are no more questions, let's all thank Manan for the talk.